Welcome to our previous year question series designed chapter and topic wise that will help you improve your score in your board exams. Question 1. The image below shows two examples of electric field lines. Which of the following statements is true? And it was asked in CBSE sample question paper 2022-23. So two figures are given to us. We can see that these are the field lines which are parallel and equispaced, and they must be originated from some positive charges that are present at this side, and they will travel to the negative charges because electric field will always originate from the positive charge and go towards the negative charge. Now let's try to examine the statements which are given to us. Statement A, the electric field in both 1 and 2 arise due to single positive point charge located somewhere on the left. So this is not the electric field lines due to a positive charge. That is only a single positive charge, because due to a single positive charge, the field lines should be like this. So none of these are representing this kind of scenario. That's why statement 1 cannot be true. Let's take statement B. The electric fields in both 1 and 2 can be created by negative charges located somewhere on the left and positive charges somewhere on the right. But we know that electric field lines, they always travel from positive to negative. So towards left, there has to be positive charge, and towards right, there has to be negative charge for both the field lines. So that's why statement B is also not true. Let's take statement C. The electric field in first is the same everywhere, but the electric field in second becomes stronger as we move from left to right. So these are the field lines which are equispaced and parallel. So equispaced and parallel, they represent uniform electric field. So this is true. And in this case, the field lines are not parallel, but they are dense towards the right and they are far apart towards the left. So towards the left side, the field is weaker, and towards the right side, they are stronger, because more be the density of field lines, more be the closeness of field lines, more be their intensity. So statement C seems true. And let's take statement D as well. As you move from left to right, the field lines in both 1 and 2 become stronger. So in case 1, the field lines, they are equispaced and parallel, they are uniform. So they are not changing when we are moving from positive to negative side or from left to right. But in case 2, they are becoming stronger when we are moving from left towards right. So this statement is not true. Only statement C is true, and that is the answer for this question. Question 2. 2-point charges plus 8q and minus 2q are located at x is equal to 0 and x is equal to L respectively. The location of a point on the x-axis at which the net electric field due to these 2-point charges is 0, that needed to be obtained. And it was asked in CBSE sample question paper 2023-24 and also in AIEEE 2005. So let us draw the scenario. This is our origin O, and at a distance L from it, we are having a point, let me call it as A. And at O, we are having plus 8q charge, and at A, we are having minus 2q charge. We need to find a point on the x-axis at which the electric field due to these two charges is 0. So let electric field is 0 at a distance x from A, that is minus 2q charge. So from this minus 2q charge, we are having a point P that is located at a distance x from it. And at point P, the electric field is 0. Now at point P, there will be two electric fields. One is because of the plus 8q charge that is located at O, and other one is because of minus 2q charge that is located at A. So let me draw those fields. So electric field at point P due to minus 2q charge, it is towards the minus charge because electric field will always move towards the negative charge. So this is electric field at point P due to charge present at A, that is EPA. And electric field at point P due to the charge present at O, it will be in a direction towards the positive x-axis because due to a positive charge, the electric field will be always away from the positive charge. So we will be having EPO, electric field at P due to charge present at O. So let's try to find out the magnitude of these two electric fields, and they has to be equal because they are opposite in direction, and when they are equal, the net field at P will be 0. So electric field at P due to charge present at A, it will be K 2q upon x square. So the distance between A and P is x. So kq by x square. Here q is 2q. And we will not be taking the minus sign into account because we have already taken the sign in the direction. So it is towards negative x-axis. This is EPA. Again, electric field at point P due to charge present at O, EPO, that will be K into 8q upon L plus x whole square, because now the distance is L plus x. So L plus x whole square, and it is towards plus x-axis. Since both the fields are in opposite direction, for the net electric field at P to be 0, they has to be equal in magnitude. So for EP to be 0, that is the net electric field at point P to be 0, we have to be having K into 2q upon x square, that has to be equal to K times 8q upon L plus x whole square. K gets cancelled out with K, Q gets cancelled out with Q. This 2 will make this 8 to be 4 here when we cancel it out. And we are having something like this, that L plus x whole square upon x square, that is equal to 4. Now if we take root both sides, we will be having L plus x upon x is equal to 2. And then when we solve it out, we will be having L plus x is equal to 2x, and this implies x is equal to L. So this is the distance of point P from A, but we need to tell the distance from the origin. So that distance will be what? So distance of point P from O will be L plus x, and x is L. So it will be L plus L, that is equal to 2L. So from origin at a distance 2L, the net electric field will be 0. And in this case, option C is correct. Question 3. An electric dipole placed in an electric field of intensity 2 multiplied by 10 to the power 5 Newton per Coulomb at an angle of 30 degree experiences a torque equal to 4 Newton meter. The charge on the dipole of dipole length 2 centimeter is. So electric field intensity, it is given to us as 2 multiplied by 10 to the power 5, and the dipole is placed at an angle theta, that is equal to 30 degree, and the torque experienced by it is 4 Newton meter, and also the dipole length, that is 2a, it is equal to 2 centimeter. So this is the scenario, plus q and minus q, and it is experiencing a torque that is equal to 4 nanometer. We need to find q. So we know this thing, that the torque tau, it is Pe sine theta, and where P is Q into 2a. So that will be Q into 2a E sine theta, that is the value of torque. Let us put the values. Torque tau, it is equal to 4 Newton meter. So 4, it is equal to Q, and 2a, it is equal to 2 centimeter. So that will be equal to 2 multiplied by 10 to the power minus 2 meter, value of electric field is 2 multiplied by 10 to the power 5 and sine theta is sine 30 degree. Now we can cancel this out and it becomes equal to 1 is equal to q times 10 to the power 3 multiplied by sine 30, that is equal to half. So we can take all other things towards that side. So this implies 2 upon 10 to the power 3 is equal to q, and we can write it as q is equal to 2 multiplied by 10 to the power minus 3, and that is equal to 2 microcoulomb. So from the given options, 2 millicoulomb, not micro. So from the given options, we are having option C as correct. Question 4. An electric dipole of dipole moment P is placed parallel to the uniform electric field. The amount of work done in rotating the dipole by 90 degree is. So theta 1 for the dipole is given to us as 0 degree. Why? Because P and E vector, they are parallel to each other. So in this scenario, the dipole is placed in such a way that the angle that it is making with the electric field is 0 degree. And theta 2 is 90 degree because we are rotating the dipole by 90 degree. So using the formula for potential energy of dipole, it is given as U is equal to P E cos theta 1 minus cos theta 2, where theta 1 is the initial angle and theta 2 is the final angle of the dipole that the dipole moment is making with the electric field. So the dipole moment is P and it is placed in an electric field that is having strength E. Theta 1 is 0, so cos 0 minus cos 90. Cos 0 is 1, cos 90 is 0, so we can write PE 1 minus 0 and that is equal to PE. So this is the potential energy of the dipole when it is rotated through an angle of 90 degree from an initial angle when it is placed parallel to the electric field, and from the given options, option B is correct. Question 5. A point charge is situated at a distance r from a short electric dipole on its axis. It experiences a force F. If the distance of the charge is 2r, that it has made 2 times the initial distance, the force on the charge will be. So this is the scenario that we are having, that there is a dipole, very short dipole of length 2a, and from this on the axial point, let's say that P is the point on its axis, and here a charge Q is placed and it is experiencing a force capital F. So we know the electric field at axial point of a short dipole, it is given as E is equal to 2kP upon r cube, and the force on the charge, it is Q times E. So what we can write is that F is equal to Q times 2kP upon r cube, where K, it is equal to 1 upon 4 pi epsilon naught, and P, it is the charge of the dipole multiplied by the distance of the dipole, that is Q into 2a. Electric dipole moment is P. Now we can see from this that F, it is proportional to 1 upon r cube. So this is the value of F when the distance was r. Now F dash, it is proportional to 2 r cube. So what we can write, F dash proportional 1 upon 8 r cube. And from these two equations, we can say that when we take the ratio, all other things will be cancelled out, and F dash, it becomes F by 8. Because when the distance is increased 2 times, the force will be reduced by 8 times. So from the given options, option B is correct. Question 6. the magnitude of the electric field due to a point charge at a distance of 4 meter is 9 Newton per Coulomb. So we are having a point charge Q, and from a distance R1, the electric field is 9 Newton per Coulomb. So let me call it this point as P. And the value of electric field at P is E1. Now we need to find a distance at which the electric field is increased to 16 Newton per Coulomb from the same charge. So what I can write, E1, it is equal to KQ upon R1 square. That is the first electric field, and value of E1 is 9 Newton per Coulomb, and R1 it is equal to 4 meter. Now I need to find R2 for an electric field E2. That will be E2 is equal to KQ upon R2 square, and E2 value is given to us as 16 Newton per Coulomb, and I need to find the value of R2. So let's take the ratio of these two electric fields. E2 ratio E1, it will be R1 square divided by R2 square. So when we divide these two equations, we are left with this. All other things will be cancelled out. Now let's put the values. E2 is 16, E1 is 9, R1 square is 4 square, and R2 square we don't know. We need to find the value of R2. Let's take square root in this equation, and we are left with 4 by 3 is equal to 4 upon R2. Square root of 4 square is 4. So this 4 gets cancelled out with this 4, and this implies R2 it is equal to 3 meter. So at a distance of 3 meter from this point charge, the electric field will be 16 Newton per Coulomb, and from the given options, option C is correct. Question 7. An electron experiences a force 1.6 multiplied by 10 to the power minus 16 Newton I cap in an electric field E vector. The value of electric field E vector is, so we need to find the value of electric field E, and it was asked in CBSE sample question paper 2021-22. So the force F vector is given to us 1.6 multiplied by 10 to the power minus 16 Newton, and it is towards the positive x-axis, that is I cap. We know that force on electron is opposite to the direction of electric field. So if electric field is towards the positive x-axis, the force will be towards the negative x-axis. So since the force is towards the positive x-axis, electric field has to be towards the negative x-axis. So we can find it out. F vector it is equal to minus Q times E vector. So we can put the values. F is what? 1.6 multiplied by 10 to the power minus 16. That is equal to the charge on electron is 1.6 multiplied by 10 to the power minus 19 Coulomb multiplied by E vector. So 1.6 gets cancelled out with 1.6, and this when goes towards the denominator, we are left with 10 to the power minus 16 divided by 10 to the power minus 19, and with a minus sign, that is E vector. And when we solve it out, we are left with 10 to the power 3 I cap Newton per Coulomb, because I cap was already there in the force formula. And this negative sign, it is because electron will experience a force in a direction opposite to that of the electric field. So electric field is towards the negative x-axis. So that is minus 10 to the power 3 I cap Newton per Coulomb. And from the given options, option B is the correct answer. And 8. Two parallel large thin metal sheets have equal surface charge densities sigma, that is equal to 26.4 multiplied by 10 to the power minus 12 Coulomb per meter square of opposite signs. The electric field between these sheets is, so we are having two sheets. One is positively charged and other one is negatively charged. And we need to find the electric field at a point between the sheets. So we know that electric field due to oppositely charged sheets in between them, it is given as E, it is equal to sigma upon epsilon naught. We know the value of sigma, it is given to us 26.4 multiplied by 10 to the power minus 12, and epsilon naught is 8.85 multiplied by 10 to the power minus 12. So this 10 to the power minus 12 gets cancelled out with this 10 to the power minus 12, and we are left with 26.4 divided by 8.85. So when we solve it out, it is approximately equal to 3 Newton per coulomb. So from the given options, option D is correct. Question 9. An electric dipole consisting of charges plus q and minus q separated by a distance L is in stable equilibrium in a uniform electric field E. The electrostatic potential energy of the dipole is. So we are having an electric field and the diode is placed in stable equilibrium. So the diode is in stable equilibrium. It means it is placed in such a way that the dipole moment is in alignment with the electric field. So this is the direction of P and this is the direction of electric field. They both are in the same direction. But remember here, the trick is the length is L, not 2L. Generally, we take the length as 2L in the derivation. And if we do it by that, we will be ending up with the wrong answer. So please remember it is L that is given to us. So now we need to find out the value of the electrostatic potential energy in this case. So we know that U is equal to minus P vector dot E vector. And when we open it, minus PE cos theta. And here theta it is equal to 0 degree because E and P both are in the same direction. So it will be equal to minus PE. And P, it is charge of the dipole multiplied by length. And here length is L, not 2L. So we'll be writing it as minus Q L E. And this is the value of the electrostatic potential energy in the stable equilibrium. So from the given options, option C is correct. Thank you. Keep learning, keep practicing, keep excelling.